This is section 10.2, day 2. Today we're going to talk about displacement and distance traveled. We really already talked about displacement earlier in the year, but this is going to talk about displacement in reference to vectors. Displacement. Recall that when a particle moves along a line with velocity v of t, the displacement or net distance traveled from time t equals a to t equals b is given by the integral. Meaning, remember when we took the integral, we didn't find position, we found the displacement, how far the object traveled. While the total distance traveled in that time interval is given by the absolute value of the function. Remember, if we have a function and it is below the x-axis, if you take the absolute value of this function, now it puts it above the x-axis. So then you're finding all positive area. Well, that's what absolute value does. When a particle moves in the plane with velocity vector v, displacement and distance traveled can be found by applying the same integrals to the vector v, although in slightly different ways. And it's very slightly, actually. Displacement and distance traveled. Suppose a particle moves along a path in the plane, so that its velocity at any time t is given by two different functions, one for x and one for y, where v1 and v2 are integrable functions of t. The displacement from t equals a to t equals b is given by, so how much they each changes is given by the integral, just like before, but we have one integral, one for the x and one for the y. The preceding vector is added to the position at time t equals a to get the position at time t equals b. The distance traveled, let's talk about that sentence. If you find out that at time t equals 3, that it's at 0.56, well, when you integrate each of these, that's displacement. So if you want to know the position, you would add 5 to this one and you'd add 6 to this one. The distance traveled from t equals a to t equals b is given by, well, we just take the absolute value of the vector, but to take the absolute value of the vector, you have to square root v1 squared plus v2 squared, and of course the integral from a to b. In exercise 37 through 40, the velocity v of a particle moving in the plane is given along with the position of the particle at t equals 0. Find a, the position of the particle at time t equals 3, and b, the distance the particle travels from t equals 0 to t equals 3. So let's look at a. We want to know the position of the particle at time t equals 3, and they tell us that they give us the position at t equals 0. So what we need to do is integrate each of these pieces from 0 to 3 of et minus t dt. But then we need to add 1 to that value. And I've actually just entered this into the calculator. It's the first line right here using f and I and t. Here's the function just with x's. And then added 1 onto the end of it. So it's 15.586. 15.586. Now, I'm sure you know how to do the integral part. I'm not worried about that because that was pretty much first semester. Now what you need to focus on is that to find the position, you have to add the position at t equals 0. Well, that's the x-coordinate. For the y-coordinate, we have 0, integral from 0 to 3 of e to the t plus t. That comes from the y part of the vector, dt, and then of course plus 1 again, but this one comes from that one. I've plugged that into the calculator as well, f and I and t, e to the t plus t, except I'm using x's, comma x, comma 0 to 3, and then of course the plus 1, and the value is 24.586. So the position is 15.586, comma 24.586. Now in letter B, it says find the distance the particle travels from t equals 0 to t equals 3. That's the integral from 0 to 3 of the square root of e to the t minus t squared plus e to the t plus t squared dt. And that comes from, here's e to the t minus t, we square that one, and then we square the y as well. That's right here. I've plugged that into the calculator as well. There's the first one, e to the t minus t squared, plus e to the t plus t squared, and of course the square root right there, comma x, comma 0 to 3, and we get 20, the total distance traveled is 27.791. In number 46, a particle moves in the plane so that its position at any time t from 0 to 2 pi is given parametrically by sine of t and cosine of 2t. So in letter A, it says find the velocity vector for the particle. So velocity equals the derivative of sine is cosine of t, and the derivative of cosine 2t is negative 2 sine of 2t. So there's the velocity vector. In letter B, it says for what values of t is the particle at rest. Now these two are independent of each other. This is the x, how x travels, and this is how y travels. We need both of them to be 0 in order for the object to be stopped, because even though the x may be 0, the y can still have a value. Now if your x is 0 and the y has a value, that just means you're going straight up. We're not going left or right, but we could still be moving. So we need both the x part of the vector and the y part of the vector to both be 0. So let's start with maybe cosine. We have cosine of t, that has to be 0. So t is the inverse cosine of 0, so we need to know where cosine is 0, but we only need from 0 to 2 pi. So we have pi over 2 and 3 pi over 2. Now that's where the x coordinate is 0, where the x is stopped. We need to know where y is stopped as well. So we have negative 2 sine of 2t equals 0. Sine of 2t equals 0, divided by negative 2. So 2t equals inverse sine of 0. So the inverse sine of 0, sine is 0 at 0, pi, 2 pi, 3 pi, 4 pi, and so on. So t equals 0, pi over 2, pi, 3 pi over 2, and 2 pi. So the two that match, both the x and the y, are stopped at when t is pi over 2 and 3 pi over 2. Letter C says write an equation for the path of the particle in terms of x and y that does not involve trigonometric functions. Well, this one is the double angle formula right here. So one of the formulas we can use for the cosine of 2t is 1 minus 2 sine squared of t. That's the double angle formula for cosine. Cosine of 2t is the y value, right there. It says y equals cosine of 2t. So we can replace cosine of 2t with y, and x is sine of t. So we can replace sine squared with x squared. Letter D asks us to sketch the path of the particle. So in my calculator, I've put sine of t into x, cosine of t into y, zoomed in a little bit, and so when we make a little sketch, this is what I expect right here. Let's see, something like that. A particle moves in the xy plane so that its position at any time t from 0 to pi is given by x of t equals t squared over 2 minus natural log of 1 plus t, and y of t equals 3 sine t. In letter A, it says sketch the path of the particle in the xy plane below. Indicate the direction of motion along the path. And let's see, I think I've plugged this into the calculator already. Let's see if it stayed in there. We have t squared over 2 minus natural log of 1 plus t. Looks like I have an extra parenthesis. I don't know if it'll really matter, but let's get that out of there. We'll delete that extra parenthesis. And the other one is 3 sine of t. So we're going to use our calculator to sketch this, and we'll pay attention to the direction that it's following. So let's graph it. All right, so it goes up to about 3 and then comes down. I wonder if we can zoom 6 and see a little bit more of that. Oh, actually, I think I had the window set to from 0 to pi. Let's take a look at that. Let's take a look at the window. So here's 0 to 2 pi, but we want t to go from 0 to pi. So good thing I looked at this. 0 to pi. Let's see what that looks like. Graph. and it kind of stops right on the y-axis. So it looks like it does this, kind of goes up to 3, and then down like that. And so the direction is this. It kind of follows this path, and we'll indicate with some arrows like we usually do. At what time t from 0 to pi does x of t attain its minimum value? What is the position x of t and y of t of the particle at this time? So we want to know what the smallest x value is. So we need to find dx dt and set it equal to 0. Derivative of t squared over 2 is t squared over 2. You bring the 2 down, you have 2 over 2t. So that is just going to be t. And then minus 1 over 1 plus t. Minus 1 over 1 plus t. Let's bring up the calculator. Let's change our mode to just function. Quit out of there. And let's put this function in, but this time we'll just be using x's. X minus 1 divided by 1 plus x. And let's zoom 6 it. Zoom 6. Well, here's the graph when we graph it, and we are looking for that value right there, where the derivative is equal to 0. So we can go second, calculate a 0. And here's the left side. Here's right bound. And let's back up. And the t value is 0.618. So t equals 0.618. Now that's the value of t when x of t is at a minimum. So it's at its minimum. What is the position x of t, y of t, the particle at this time? So now I have to plug 0.618 into the original function. So let's do that. So let's get out of here. We have 0.618 squared. We'll divide that by 2. And then minus the natural log of 1.618. And survey says negative 0.29. So the x of t is actually negative, what was it? Negative 0.29. I don't want that. 0.29. And the y value, let's go back up, and it is the 3 times the sine of the value. So 3 times sine of 0.618. Enter 1.738. 1.738. I can bring this up. At what time t from 0 to pi is the particle on the y-axis? Find the speed and the acceleration vector of the particle at this time. So at what time t is the particle on the y-axis? Well, I know I'm on the y-axis when the x-coordinate is 0. So I need to find out where this function is 0. Let's just plug that into our calculator. So we have y equals, clear this out, x squared divided by 2 minus natural log of, I don't need an extra parenthesis, x plus 1. We'll graph this and we'll find out where x is 0. And it looks like at this little tiny area here, so let's zoom in on that. Zoom in right there. Let's see if we can have a good look here. And there it is right there. So that's where we'll be on the y-axis. That'll be the value of t. We'll calculate a 0. And we need to be on the left side. And then I need to get onto the right side. We'll back up. And the value is 1.286. So t equals 1.286. At what time t? That's the value. Find the speed and the acceleration vector of the particle at this time. Well, speed is the same as the magnitude of the vector, which is the square root of x of t squared plus y of t squared, and speed is a scalar. It is a value. So I need to plug 1.286 into the original functions and square them. So to find the speed, I want to get out of here. We need to take the square root of, let's see, I need that value that I had. I need to remember it. It is 1.286. I'll make a note of that. 1.286. So 1.286 squared, I'm plugging it into this function right here, divided by 2 minus the natural log of 1.286 plus 1, and I need to square that. There's x of t squared, and then plus y of t squared. So then we have 3 times the sine of 1.286. And the answer is 1.739. 1.739. Now to find the acceleration vector, we just have to take the derivative twice. So the velocity vector, I don't know if I found that at all, I have not, is actually, where did we do that? This is the one right here. So I need to take the derivative of this right here, which is 1 plus 1 over 1 plus t squared, comma, and then the derivative of y of t is 3 cosine t. There's velocity. I have to take the derivative one more time here, so the acceleration is negative, what would it be? 1 plus t to the negative 2. So negative 2 over 1 plus t to the third, comma, and then we have negative 3 sine of t.